you might have seen some videos of ChatGPT and DeepSeek models trying to play chess, and it usually ends in disaster. While the first few moves start out pretty normally, eventually the bots lose track of where are the pieces, and soon you see them flying across the board or teleporting through each other. However, DeepSeek recently released their R1 model for advanced reasoning capabilities. This model is trained through reinforcement learning using a new technique called GRPO, or Group Relative Policy Optimization. My name is Bai. I'm a machine learning engineer and a PhD in natural language processing. In this video, I will show you how to use the same reinforcement learning techniques as in DeepSeek R1 to train an LLM to play chess. And I mean actual legal chess moves, none of these pieces flying across the board business. Before we continue, let me share something I've been working on. VoiceWriter is a tool to help you write faster using voice. Simply speak your thoughts, and the AI will fix your grammar and add punctuation in real time. It uses advanced speech recognition models, and I use it every day to write things much faster, including my emails and my daily stand-up updates. You can also use our Chrome extension to use VoiceWriter on any website. Try it for free at voicewriter.io. Now back to the video. There are several ways you can train a model to play chess. There's an AlphaZero self-play approach, where the model learns by playing against itself millions of times. But for this video, I'm going to be taking a different approach. Instead, we will make the LLM mimic Stockfish, which is the strongest rated chess computer right now, with an ELO of over 3000, so this is stronger than any human Grandmaster. To do this, we're going to get chess positions and feed them into the LLM. The LLM is going to look at this position and analyze the threats, material, the tactics, the position, etc. for both itself and the opponent through chain of thought reasoning. At the end of this reasoning, it's going to propose what it thinks is the best move. And since LLMs can be sampled non-deterministically, we can run this multiple times to get different chains of reasoning, and each of them will lead to different moves. But how will it know which move is the correct one? That's where Stockfish comes in. We're going to use Stockfish to rate each of the proposed moves. In this position, Stockfish thinks the move knight takes d5 has a score of 0.8, whereas the move bishop g2 has a score of -2.4. So knight takes d5 is a better move according to Stockfish, and we're going to use reinforcement learning so that the chain of thought that produced knight takes d5 will be more likely to be generated in the future, and the chain of thought that led to the worst move is going to be less likely to be generated. Here's how we're going to score a move using Stockfish. In this position, Stockfish thinks the best move is g3, so this move will get a score of 10. On the other hand, the worst possible legal move in this position is queen to d3. It's the only move that hangs the queen, and if we play this move, then this move gets awarded a score of 1 out of 10. Every other move gets a normalized score between 1 to 10, so for example, bishop takes a6. This move is pretty bad, since it loses a bishop, but it's not as bad as losing a queen, so this move gets a score somewhere between 1 and 10. And finally, if the model proposes an illegal move like bishop to e5, then it gets a score of 0. So this way, we teach the model to produce a legal move and preferably the best move. To get some realistic looking chess positions, I use the Lichess database, which contains millions of games available to download. I then sampled 10,000 different games and randomly extracted a position from each of the games. And this produces a list of completely random positions that are realistic to train with. First of all, I wanted to test how good were existing models at reasoning about chess. To do this, I tested the GPT-4o, the O1 reasoning model, and the DeepSeek R1 models. In this position, Black has just played queen to g4. We're white, what should we do, and what's going on in this position? If you look at this position, Black is threatening queen takes g2 mate, and we can defend this with bishop to f1. After this, there's no great way for Black to continue the attack. At the same time, we're attacking several pieces on our own, and Black has no good way to defend all of them. So if we play bishop to f1, then we should be winning. And if we turn on Stockfish, then the engine agrees that bishop f1 is the only winning move, and every other move is losing. This is a fairly straightforward position, and I think any intermediate level player should be able to find this. Here's a prompt I used. I gave the chess position in FEN format and also a graphical ASCII version of the position, just in case it's easier to work with. Black has just played queen g4, suggest some candidate moves for white, and estimate the engine evaluation for each one. First, let's see how DeepSeek R1 does. These are the 4 moves that were preferred by DeepSeek R1, and we see it does not do very well. The first move it prefers is knight to h4, attacking queen g4. So this doesn't really make sense. Not to mention it loses a knight for free. The second move is the correct one, though. It found bishop f1 as the second move. It also suggested rook e4, blocks the queen's path to e2, which also doesn't really make sense. And the last move, queen to g3, is just illegal, moving through 2 pieces. So DeepSeek R1's understanding of chess is not great. When we give the same question to O1, it does a little bit better. And O1 actually suggests bishop f1 as the top move. However, it then suggests the continuation being bishop takes g2 and then king takes g2, which is not legal. And the second best option it proposes that it thinks is approximately equal is rook to e4. The reason being that this move hits the black queen, causing it to move, which is incorrect because the queen can just deliver checkmate. So both models suggested the correct move some of the time, but the reasoning was all over the place, and they were also suggesting illegal moves and ideas that didn't make any sense. This is despite having impressive capabilities in many other domains. They're just not very good at reasoning about chess positions. So I am thinking, if we train a model specifically to optimize for chess reasoning, maybe it will perform better. Let's try to find out. So which DeepSeek model should we train? The main DeepSeek R1 model is over 600 billion parameters, and this is simply out of the question. I have a gaming GPU that has 12 gigabytes of video memory, and from experience, the biggest model that I can run is maybe 7 to 8 billion parameters. That means the distilled version of DeepSeek R1 from LLaMA with 8 billion parameters is a good candidate. I tried feeding a chess position into this model, but the problem was it would reason for way too long without ever producing an answer. Since my system does not have too much resources, I don't want a model that would reason for thousands of tokens. It will simply run out of memory before producing an answer, and there doesn't seem to be any way to limit the amount of reasoning that it does right now. So for this task, the distilled R1 models is probably not the best choice. So I went on OpenRouter and tested a few different models that were around 7 to 8 billion parameters. All of the open models, including LLaMA, Mistral, and Qwen, they all have some kind of model around this 7 to 8 billion parameter range. Remember that the base model is not supposed to already have reasoning capabilities. For reinforcement learning purposes, the ideal base model should be able to follow instructions and try to reason and get the correct answer at least some of the time. The point of reinforcement learning is to reward it when it gets the correct answer, so it does the correct type of reasoning more often. I fed a position into these models, and none of them particularly stood out as being any better than the others. They all seem to have some knowledge of how chess works, but none of them were able to produce a legal move from this position. So I decided to try both the LLaMA and the Qwen models, since they were at least able to produce output in the right format. For model training, I used a combination of the TRL and Unsloth libraries. TRL stands for Transformer Reinforcement Learning and is a library built by Hugging Face, and it implements many reinforcement learning algorithms, including GRPO for large language models. Unsloth is a relatively new library that makes some of these transformers fine-tuning operations more efficient using techniques such as improved memory management, QLoRa, and VLLM. For many of its reinforcement learning algorithms, including GRPO, Unsloth leverages the implementation from other libraries like Hugging Face TRL and patches them to be more efficient instead of re-implementing it themselves. This library does some stuff that honestly looks like dark magic to me, like using string concatenation to inject their own quantization functions into Hugging Face classes, and then using eval on these strings to load these classes into memory. So probably not the most lawful library out there, but it saves some GPU memory, so I'm like, whatever, let's go with it. I will briefly mention one technique that is pretty important for fine-tuning large models on a small GPU, and it's called LoRA, or low-rank adaptation. The idea for LoRA is we can approximate any matrix with an outer product of 2 smaller matrices. So if your matrix is like 1000 by 1000, you might only use 10 as a rank of the matrices to approximate. So you can write this 1000 by 1000 matrix into a product of 1000 by 10 and a 10 by 1000 matrix. And doing it this way requires only 2% of the parameters as the full matrix. In the LoRA method, we still keep all the pre-trained weights as a full matrix, but then this low rank approximation is used to represent the fine-tuned part. And then the fine-tuned matrix is basically added onto the pre-trained matrix to represent the fine-tuning process. And in the QLoRA method, we also use quantization to represent these pre-trained weights using 4 bits per float. And we use a slightly higher 16-bit floating point format to represent the fine-tuned parameters. So it's a careful balance between making this model small enough to train on your GPU versus not sacrificing too much accuracy. Unsloth provides a few Colab notebooks to help you get started with training GRPO on some 8 billion parameter models like LLaMA 3.1. This notebook shows you how to train GRPO on a dataset called GSM8K. And what this dataset is a bunch of grade school math questions. So some word problems that involve math at maybe a middle school level that's not very difficult. And each one of them has an answer that's an integer. They define some reward functions that give a small reward if the model outputs in the correct format. But then to get the highest possible reward, it needs to actually respond with the correct answer. If you run this training for a few hours, you can see the reward function improve. And at the end, the model is able to get these questions right a decent number of the time. In my case, I designed some similar reward functions. I rewarded the model if it used the right reasoning tags, gave it some more reward if it output the best move, and even more if the move is a valid move in algebraic notation. And finally, the score that's given by Stockfish, normalized of course to produce something between 1 and 10. Now let's talk about GRPO, or Group Relative Policy Optimization. And this is a new technique that was introduced in one of the DeepSeek papers. This is a reinforcement learning method, and it improves on PPO, which was previously one of the most popular algorithms for reinforcement learning. But the issue with PPO is it's quite complicated. So in a PPO setup, you have the policy model, which is the model that you're currently trying to train. But then you also have several other models. The reference model is a sort of baseline model that the policy model is not supposed to deviate away too much from. You have the reward model that's supposed to assign a reward once the policy model has generated a sequence of outputs. And the part that I think is confusing to a lot of people is the value model. And this is the part that GRPO is trying to avoid having. The value model is kind of like a reward model, but instead of judging it at the end of a sequence, it gives a score to like each intermediate token of the sequence as it's generating. So it's a regression model that predicts what's called the advantage function, which is, you can think of it as a smooth version of the reward. The reference and reward models are not too bad because at least they're frozen, so we don't need to update them during training. But in PPO, the value model needs to be trained at the same time as the policy model. So you have two models that are both large language models, and for one model to be optimized correctly depends on the other one being trained at the same time. So as you can imagine, this can get quite complicated. Here's another diagram of the PPO setup, and you can see there's a lot of moving parts and a lot of details that can go wrong. But I won't talk too much about PPO because this video is about GRPO. And with GRPO, what they're saying is we don't really need the value model. Instead of training a special model to give feedback to the policy model, what if we just run the policy model multiple times? And each output from the group is given a different reward. And some of these rewards will be higher and some of will be lower. And we can just normalize the rewards to give feedback back to the policy model. So what will this look like in our setup? Let's just add 3 more generations. So we have 5 random generations from the given position. The reward model first gives a score for each of the generations. And then GRPO just normalizes and standardizes these rewards to get the advantages for each of these generations. And the more positive is the advantage, it means this output is good. So the model should do more of this in the future. Whereas a negative advantage means whatever you did, it's incorrect. So please stop doing this in the future. So that's how we use the group rewards to update the policy model. Coming back, the reward model is just stockfish, so it's not really a model. So all we are left with really is the policy model that we are trying to train. And we still need the reference model to not deviate too much from, and this is good for stability reasons. But this one is not too bad because it's frozen, so it's only one trainable model in GRPO. But the disadvantage is you have to generate multiple times randomly with each input, whereas in PPO you only need to generate once per input. Here are the numbers that are used in DeepSeek R1's training, and they use a group size of 64. So every time, every input they will generate 64 outputs to compare against each other. If you're trying to train this at home though, you're gonna have to make some compromises. And I basically just used the recommendation set of parameters recommended by the Unsloth library. They recommend a group size of 6 and a batch size of 1. So some compromises will be needed to get this to work on one GPU. Our maximum sequence length is also going to be relatively limited due to the memory constraints. The DeepSeek R1 model is trained with a relatively long sequence length of 32,000, and you can see in the training run that as the model trains, the average length of its responses grows larger and larger, and it's around 10,000 by the time it's done training. And practically that means if your sequence length is relatively limited, like 512, then you can't really run the DeepSeek model, and it will never finish generating before your sequence length is reached. But we avoid this problem if we start with LLaMA 8B or any base model that didn't already learn to reason for this many tokens. But anyways, this is a setup I used, and I left it training for a few days, so let's see what happens. I added some logging into TensorBoard so we can see what the model is doing. First, the model was able to consistently output the correct format almost all of the time, with the formatting reward function reaching near the max value of 0.5. Scrolling down, we see that the stockfish reward function starts out pretty low at around 1, dips a little bit, and soon plateaus at a value of around 4 or 4.5. This means it's able to suggest okay moves at least some of the time, and much better than a base model, whose moves is almost never a legal move. Looking at the moves though, it seems to really like pawn moves, specifically moving the A pawn. The most common moves that it plays is A4 as white and A5 as black. So in other words, pushing the A pawn at the side of the board, usually 2 squares, but sometimes 1 square as well. I confirmed this by plotting a distribution of the moves it makes as white and as black. Over 80% of the time, for both sides, it chose to push the A pawn. We know that this is something that was learned during training because the base model before training prefers different moves like bishop c4 as white and knight c6 as black. But the model quickly learned that these moves were not as good as a4 and a5. Let's analyze why did this happen. In many middle game positions, moving the a pawn is not such a terrible move, and in this case it's one of the best moves by Stockfish, so it gets a score of 9.5. Even when it's not a great move, it's often a legal move, just kind of by accident. Like in this position, a4 is a legal move by white, and a5 is also a legal move by black, as long as the king is not in check and these pawns haven't moved, which oftentimes they don't for most of the game. And here, a4 is not a great move because there is a knight hanging, but it's also a legal move and it doesn't lose the game, so Stockfish gives this move a score of 6.2. Of course, we can't always get lucky, and sometimes a4 is not going to be a legal move and gets a score of 0. And if you look at the reasoning, it never really makes sense either. Like the model just says some words about chess and then makes the move a4. Like here, it says white rook is on the same file as a black king, which is obviously not true. And even if this were true, it has nothing to do with the move a4. So I guess what's happening is the model doesn't really know how to interpret the board position, and it probably doesn't even know how the pieces move. But it has figured out how to extract the information of whose turn is it to move, and the best move given just this information is either a4 or a5. I tried doing the same experiment, but with the Qwen 7b instruct model instead of the LLaMA model, and it got a pretty similar result, except that instead of pushing the A pawn, like A4 and A5, it instead converged on H4 and H5. This is despite the distribution of moves that it tends to generate before any training is pretty different from LLaMA. Like the base model tends to play a lot of rook takes d5 and rook takes d7. And these are almost never legal moves, so the model quickly learns to not play these moves and instead play h4 and h5. And in the end, the Qwen model converged to around the same score as the LLaMA model. But the training was a little bit slower because in the beginning it was always playing like rook takes d5, which is almost never a legal move. But eventually I figured out that the best move to play is h4 and h5. I am a little bit disappointed at this negative result, but let's see if we can analyze what happened and why didn't this work. The first clue comes from one of the Deepseek papers. It says it seems that the improvement is attributed to boosting the correct response from top K rather than the enhancement of fundamental capabilities. In other words, if we start with a model that gets the answer some of the time, then applying RL makes it get the right answer more consistently. But reinforcement learning is not able to enhance the fundamental capabilities. So if the model doesn't even know how the pieces move, then there is no way that it can learn through RL. Like I gave it a simple test. If I have a knight on b6, which are the squares it can move? And LLaMA gave the response of a4, c4, a5, c5, d3, and f3, which is not even close to the correct answer, so it doesn't really know how the pieces move. I tried the same question on some bigger models like GPT-4o, and it is able to get this correct. So I think trying this reinforcement learning technique on a bigger model would be more successful, especially with a model like GPT R1, which we've seen before is able to get the right move some of the time. Then I think GRPO would be a good way to get this model to be more consistent and get the right move more often. There is another interesting point in the DeepSeek R1 paper about training reinforcement learning on larger and smaller models. They tried training a 32 billion parameter model, and what they found was that it didn't really work. After large-scale RL training, it achieves performance on par with the base model. So in the results table, when they trained the 32 billion parameter model, the accuracy for before and after RL is basically the same. Instead, what they found that worked better was training a large model using RL and then using model distillation. Distilling more powerful models into smaller ones yields excellent results. So you have to first train a larger model and then use model distillation to get a smaller model that can reason. Even the DeepSeek people were not able to get a small model to learn to reason. So there's a good chance that this is an issue of scale, and if we just repeated the same experiment on a much bigger model, then this will work better. But unfortunately, training these 100 billion parameter models is far out of reach for most people, and is only possible in a few research labs that have this type of infrastructure. Before I end this video, I'll quickly go over some other interesting things happening with language models and chess. You probably already know about AlphaZero, which is a neural network by Deepmind that can play chess, sometimes even better than Stockfish, using a technique called Monte Carlo tree search. This paper from Deepmind trains a neural network that plays chess without doing any tree search, and it trains it in a supervised way, similar to the way that I did with getting it to copy the moves that are suggested by Stockfish. And it's able to reach a Lichess elo of over 2800, so around a Grandmaster-level. And the model that it trains is not even that big by today's standards, around 270 million, so not even 1 billion parameters. Initially I assumed it's probably using some kind of special architecture that's more suitable for chess than the transformer architecture, right? Here's the architecture that's used in AlphaZero, and it has a lot of things that you typically see in computer vision, like these convolutional blocks and residual networks. So is architecture the key difference? But if you look at the paper, then you see that no, not really. They just trained a vanilla transformer using more or less the same architecture as LLaMA. Then what's the difference? Why is this model able to play at a Grandmaster level when other models like GPT-4 struggle so much? Well, a big difference lies in the way that they set up the tokenizer. Here is a typical position in FEN format, and it's not a really nice format for language models to work with. When you see a number like 8, that means the entire row is empty. And this row here means we have 3 white pawns, 2 empty spaces, and then 3 more white pawns. But it's all kind of jumbled up because these 3 pawns is treated as 1 token, and then this new line and the rook is treated as 1 token. So the Deepmind paper decided to pad the FEN to be a constant length. This way the input is always exactly 77 characters, and they set up the tokenizer so 1 character is always 1 token. So all the positions are fixed, like this token here. This position will always be, maybe the D4 square. So if you have a capital P on this position, then you know that there is a white pawn on D4. Tokenizing this way is helpful for the model to quickly learn what are the relationships between the squares of the board and which pieces can move where. And this position is fed into the transformer model, which generates a move token. So it's not a typical auto-regressive language model because it just goes in 1 forward pass and generates 1 output. And to output the move, they encode every possible move in UCI format, like E2, E4. Each possible move is considered its own token. And they realized that if you represent moves like this, then there are only about 1,900 possible different moves. And it's easy to check which one of these moves are legal using Stockfish and make sure that you always generate a legal move. So yes, they technically did use a transformer, but they also set up the architecture in a very specific way for it to learn chess quickly. The downside is it doesn't have any concept of language, so it will never be able to tell you why it made a certain move. So training a more general purpose large language model to play chess at a high strength, I think will be more challenging because the tokenizer cannot be specialized for chess. It needs to be able to deal with language as well. Now back to the world of language models. A recent paper that tries to make it play chess better is called ChessGPT. And in this paper, they got a whole bunch of chess data from all kinds of YouTube videos, blogs, forums, etc. And they use it to train a language model that's similar to the LLaMA architecture. So they first did some pre-training on all this chess data, and then they did some instruction fine-tuning. And they have a bunch of different results. For example, their model is able to keep track of what's happening in a chess game with over 90% accuracy, even when the game is pretty long. And given a chess position, the model is able to find mate in 1 about 70% of the time. This result is okay, but definitely not at a Grandmaster level. Some people have also noticed that there is something weird happening with LLM and chess, and there is one very specific model called GPT 3.5 Turbo Instruct that can play chess way better than any other model that came after it, including like GPT 4.0 and GPT 0.1. The way that you have to use this model is a bit unusual now. You have to give it the game up to this point in PGN format and ask it to play what's the most likely next move. So you cannot just give it a random position and ask it to find the best move. Apparently the model also plays better if you start by saying that this is a game between 2 famous grandmasters. Anyways, some people have claimed that this model can play at a rating of around 1750, so pretty good. But we might never know what is it exactly about this specific model from 2023 that makes it so good at chess, at least so much better than every other large language model. And when I tried running this model with the API, I can say that it plays chess decently well, but I can't quite explain why it made any of these moves. Like if you ask it to generate an explanation, then the explanation doesn't make any sense. Anyways, that's all I have for this video. I hope that pretty soon we'll be able to play a decent game of chess against a large language model that can also explain what it's thinking about in natural language. It took me a lot of time to run all these experiments and make this video, so if you made it this far, please like this video and subscribe to my channel if you haven't already, and ring the bell icon to get notified when I make similar videos like this. That's it. Goodbye.